Welcome back to the deep dive. We have a really interesting stack of documents on the table today.
We do.
And it's interesting because we are doing something we rarely get to do. Usually we're archaeologists. We're digging through history, analyzing established science, or maybe reviewing books that have already hit the bestseller lists.
Things that are set in stone, basically.
Exactly, set in stone. But today we're acting as futurists.
Or maybe meteorologists would be the more accurate analogy.
I like that better, yeah. Meteorologist. Think of this deep dive, for everyone listening, as a security weather forecast. We aren't looking at the storms that, flooded the basement 5 years ago. We aren't even looking at the rain that's falling outside the window right now.
Yeah, this is all about what's coming.
We are looking at the radar. We are specifically scanning for the storm clouds that are gathering on the horizon for the year 2025.
And in the world of cybersecurity, that distinction is, well, it's absolutely everything. If you're building your digital defenses based on what was a threat in 2021 or even last year,
you're already behind.
You are already losing. You're effectively fighting the last war, while the adversary has moved on to completely new tactics, new weapons, and frankly, new battlefields.
So let's ground everyone in our source material for today. We are analyzing a document that's framed as an evolution and analysis report.
Right.
It's a comparative study. It looks at the well-established risks of 2021, and it contrasts them with the emerging risks projected for 2025. It's essentially a roadmap of where the digital ground is shifting under our feet.
But we have to lead with a very important caveat here.
A huge one. The massive flashing red warning light from the source.
We do, and I want to be incredibly precise here so no one listening gets the wrong idea.
Okay.
The official OWASP Top 10 for 2025 has not been finally released as a signed, sealed, delivered standard yet.
So this is not etched in stone tablets?
Not at all. What we are breaking down today is a proposed list. It's based on community trends, it's based on extensive survey data, and maybe most importantly, the raw telemetry that security researchers are seeing on the ground right now.
Okay, so we shouldn't treat this as the final gospel of security.
Exactly. Do not treat it as gospel. Treat it as a compass.
A compass.
It's showing us the expected direction. It helps us answer the most expensive question in all of software development, which is, where should we be spending our budget and building our walls next year?
Because if you wait for those final stone tablets,
you might be 2 years too late. The storm's already hit.
And that is our mission for this deep dive. We're going to decode this shift in the digital landscape. We need to understand why some threats are, rising up the charts, why others are falling. And this is the part that really hooked me. We need to talk about the brand new entries. There are things on this 2025 list that didn't even make the top 10 before, which to me suggests a fundamental change in how we build technology.
That's where the real story is. The new entrants aren't just, new bugs. They are symptoms of a changing ecosystem. They tell us how the nature of building software has evolved from the era of I write code to the era of I assemble clouds.
I like that. I assemble clouds. So we have a roadmap to get through. We're going to break down this list one by one. We're going to focus heavily on the new heavy hitters in cloud and supply chain.
The big ones.
And because I know we have a lot of builders and breakers listening, we're going to end with a bug bounty perspective. Literally, where is the money hiding in 2025? If you want to get paid to break things, where should you be looking?
It's going to be a fascinating ride. I'm excited.
All right, let's unpack this. Let's start at the very top. The undisputed king of vulnerabilities, segment 1, broken access control, or as the list categorizes it, AO1.
It's funny. The more things change, the more they stay the same. AO1 retains the #1 spot from the previous list. It was the king in 2021, and all the data, all the surveys project it to still be the king in 2025.
The source material had a phrase that I thought was great. It translated roughly to still the most dangerous risk.
It is. It's persistent.
But I want to make sure we are all on the same page. For the listener who might be a manager or a product owner, not necessarily a coder, can we define broken access control in plain English? Because it sounds a bit like broken lock. But I feel like it's more nuanced than that.
It is slightly more nuanced. And you're right, the name can be a bit jargony. Put simply, broken access control is letting the user do something they are not allowed to do.
Okay.
Let's use a physical analogy. Imagine you have a key card that opens the front door of your office building. That's fine. You are an employee. You have the right to enter the building. That part is authentication. We know who you are. We verified your identity.
Okay, so I'm in the lobby. My identity is confirmed.
Right, you're in. But broken access control is when that same key card, which should only get you into the lobby and maybe your own cubicle, also opens the CEO's office, the server room, and the company's safe.
So it's not that I hacked the lock or, picked it with a wire.
Not at all.
It's that the system just let me in.
Precisely. The system didn't check the permissions on those specific doors. It just saw valid card, and the logic was open. It verified who you were. It knows you are the host, but it failed to verify if you specifically had the right to be in the server room.
It confused identity with permission.
That's the perfect way to put it. It confused identity with permission.
That sounds incredibly basic. Like, that's Security 101, isn't it?
Yeah.
Can you give us a concrete example of what this looks like in a modern web app? Because I assume it's not always as obvious as a door just swinging open.
It can be surprisingly obvious. I mean, the most classic example is a normal user managing to access admin APIs or pages.
Okay, walk me through that.
Imagine a normal user logs into an e-commerce site to buy some shoes. They see their dashboard URL in the browser bar. Maybe it ends in something like user dashboard.
Okay, standard stuff. I see that all the time.
Now, if that user is a little curious or maybe a little malicious, they might just click on the URL bar, backspace over the word dashboard, and just type admin.
And just
Hit enter.
hit enter.
Yeah.
If the application has broken access control, the admin page just loads. No warning, no error.
Yeah.
Suddenly, a regular customer is looking at the user management screen for the whole site.
Oh, wow.
They can delete other users, they can change product prices, see sales data, or maybe even refund their own orders.
It seems almost too simple to be the #1 threat in the entire world. You're saying the system doesn't bother to check, hey, is this person an admin, before it loads the admin page?
In a vulnerable application, no, it doesn't. It just checks, is this person logged in? And since the answer is yes, it serves the page, the authorization check is just missing.
And that's just one way. There's a more subtle version too, right?
Oh, yeah. And this is perhaps the more dangerous and common version. It's called IDOR, Insecure Direct Object References.
I love that acronym, IDOR. It sounds like a villain from a fantasy novel. The great IDOR demands your data.
It does have a menacing ring to it, doesn't it?
Mm-hmm.
But it's actually very common and very, very stealthy.
So what is it? Let's say you log into your online bank or a medical portal. Look up at the URL in your browser. You might see something like accounted 1001. That number, 1001, implies that in the database, you are row number 1011.
Okay, I see that kind of structure all the time. Ordered, userid, invoice side, that kind of thing.
Right. An IDOR vulnerability happens if you, the user, simply change that number in the URL from 1001 to 1002 and hit enter.
And what's supposed to happen?
Ideally. You should get a big fat error saying access denied or forbidden. The system should check, okay, this person is user 1001. Are they allowed to see data for 1002? The answer should be no.
But in an IDOR scenario.
In an IDOR scenario, the system shows you user 1002's data.
Oh, no.
You see their credit card info, their medical records, their home address, all of it. The system checked that you were logged in, but it didn't check if user 1001 is authorized to look at user 1002's file.
That is terrifyingly easy to execute. You don't need special hacking tools for that. You just need a web browser and a little bit of curiosity.
You're right.
You could essentially just walk through the entire database, 1003, 1004, 1005.
Exactly. This is often how massive data leaks happen. Someone writes a very simple script to just cycle through every number from 1 to 1,000,000, and they scrape the entire user database without ever hacking a single password.
Which brings us to the really big question, the why. Why is this still #1? Why haven't we fixed this yet? We've known about this specific class of bug for decades.
The source is very, very clear on this. Authorization bugs are simply found the most frequently in real-world applications. They are ubiquitous.
But why?
And the reason is that they're hard to automate.
Hard to automate. I thought we had scanners for everything these days. Static analysis, dynamic analysis.
We do, but think about it from the computer's perspective. A computer knows if code crashes, that's a syntax error. A computer can see a SQL injection pattern. But does a computer know that user A shouldn't see user B's file? To a computer or an automated scanner, the request looks perfectly valid. The user asked for file 1002. I gave them file 1002. The transaction was successful. It returns an HTTP 200 OK status. Everything looks green.
I see. The computer doesn't understand the intent or the business relationship between the users. It doesn't know the rules of the business.
Exactly. It takes a human understanding of the business logic to realize that was a catastrophic privacy breach, and that's why it stays at #1. It requires careful manual design and thoughtful testing, not just a simple software patch. You have to design the permissions model correctly from day one.
So the king keeps his ground because he's hard to dethrone without actual human intervention.
That's a great way to put it.
But let's move to the next segment because this is where things really start to shake up. We have a riser, a massive mover on the chart.
Yes, AO2, security misconfiguration.
This one jumped from number 5 in the previous list all the way up to number 2 for 2025. That is a significant leap. Usually these lists move very slowly. What is driving this sudden spike?
This is really the story of our time in tech. And first, let's define it clearly. Security misconfiguration isn't necessarily a bug in the code that a developer writes.
Okay.
You could write the most perfect, secure C++ or Python code in the world. Your logic could be flawless. But if the server or the cloud environment or the application framework is configured incorrectly, you are wide open. It's a setup bug.
So to go back to our bank analogy, it's like buying a top-of-the-line bank vault, installing it perfectly, verifying the steel is 6 inches thick, but then leaving the factory default combination of 0000 on the dial.
That is the perfect analogy, and you'd be absolutely shocked how often that happens digitally. Or, to extend the analogy, imagine you bought that vault, but you left the installation manual sitting right next to it, and on page 3, it lists the master reset code.
Okay, so what are the culprits here? What are the digital equivalents of leaving the manual out? What are we seeing in the wild that's causing this spike?
The source lists a few distinct and very common types. One of the biggest is leaving debug mode on in a production environment.
Debug mode? That sounds like something that should be strictly restricted to a developer's laptop.
It absolutely should be. When an app is in debug mode, if it crashes, it doesn't just show a friendly, oops, something went wrong message. No, it spits out huge amounts of internal information. We're talking database structures, file paths on the server, memory dumps, sometimes even secret keys and environment variables, all designed to help the developer fix the problem.
Which is great for the developer at 2 a.m. on a Tuesday trying to fix a critical bug.
Exactly. But if a regular user, or worse, a hacker, sees that on a live website, it's a goldmine. It's like leaving the architectural blueprints of the bank on the lobby floor with a big red X marking the spot where the cameras have blind spots.
The source also mentioned expose.env files.
Yeah.
I feel like I hear about this constantly in tech news.
Right, and this is a huge one. Modern apps use these environment files, usually just called .env, to store all their secrets.
Like
API keys, database passwords, credentials to talk to cloud services, all the keys to the kingdom. They're supposed to be completely hidden on the server, never accessible from the outside.
Right.
But if the web server is misconfigured to allow the public to read that file, which happens shockingly often, the attacker doesn't need to hack anything. They just go to their browser and type website.com.env and the file downloads.
You're kidding.
Not at all. They download the file, take the keys, and now they can log in as the administrator to your database or your cloud account.
It's literally just handing over the keys to the castle.
Yeah.
And of course, the classic one, default credential.
Yes. Admin, root password. Every router, every IoT camera, every piece of enterprise software ships with defaults. If you deploy them without changing those credentials, you are vulnerable instantly.
There are bots scanning for this, right?
Constantly. There are automated bots scanning the entire internet 24/7, just trying admin, and a list of other common defaults on every IP address they find.
But here's the big question. Why did this jump to number 2? We've always had default passwords. Debug mode has been around forever. Why is this risk exploding now?
The source explicitly, and I think correctly, blames the rise of cloud and DevOps mistakes.
Okay, let's unpack that. Why does the cloud make this worse? I thought the cloud was supposed to be more secure.
The cloud can be more secure, but it is infinitely more complex. Think about the old days. You had one physical server sitting in a closet in your office.
Right.
You configured it once, you locked the door, and maybe you walked away for 5 years. Today, with the cloud, infrastructure is code. You are spinning up hundreds of servers, databases, storage buckets, and serverless functions instantly using scripts.
So the complexity has just exploded. You aren't managing one server, you're managing an entire dynamic fleet.
Exponentially. You have AWS, Azure, Google Cloud. All of them have thousands of different settings and permissions. One single tick box left unchecked on an Amazon S3 storage bucket, and suddenly your entire customer database is public to the entire world.
And because it's automated?
And because we are using automation, DevOps tools, to deploy these servers, if you make one mistake in that script, you don't just create one insecure server.
You create 1,000 of them.
You create 1,000 insecure servers in seconds. The automation scales your mistakes.
It's the downside of all that speed and scale. We can build faster than ever, but we can also leave doors open faster than ever.
And that actually brings us perfectly to segment 3. If AO2 is about the environment we build in, AO3 is about the materials we build with. And this is a true headline moment for the 2025 list.
Yes, AO3, software supply chain failures. The source marks this as a brand new category and labels it as very important.
This is, in my view, the single biggest shift in the security mindset for 2025. It changes the game completely. It acknowledges that we aren't just writing code anymore, we are inheriting code.
The source used a phrase that really stuck with me. It essentially said, your app might be safe, but the dependency is malicious.
And that right there is the nightmare scenario for every modern developer.
Let's break down the concept. What do we mean by dependency or supply chain in this context?
So, modern software isn't written from scratch. It's assembled. If you are building a car, you don't smelt the steel yourself, you don't mold the tires, and you don't blow the glass for the windshield.
Right, you buy parts from other companies.
You buy the tires from Michelin, the glass from Saint-Gobain, the electronics from Bosch. In software, these parts are called libraries or packages or dependencies.
So I'm writing my code, and I need a function to, I don't know, calculate a date or process a credit card. I don't write all that complex logic myself.
No, why would you? It would take months. You just download a date calculator package or a credit card processor package from the internet.
From public repositories, right?
Yeah.
Like NPM or PyPI.
Exactly. You pull it from public repositories like NPM for Node.js or PyPI for Python. You trust that code. You import it into your project because it saves you an enormous amount of time. A typical modern application might have, say, a few thousand lines of its own code and millions of lines of dependency code.
And the nightmare scenario is?
The nightmare is that the date calculator package you downloaded has been poisoned. Maybe the original person who maintains it got hacked. Maybe they sold the project to a criminal group. Maybe a rogue employee at the company that created the library inserted a backdoor.
So I download this innocent-looking helper tool.
You write your perfect secure code, you import the library, and the moment you run your app, that library quietly wakes up in the background and starts sending all your customer data to a server in a hostile country.
Or it starts mining cryptocurrency using my server.
Or that. Or it installs ransomware. The possibilities are endless.
So you, the developer, did nothing wrong in your own logic. You were just betrayed by your supply chain.
Correct. And the source gives very specific examples here. Compromised packages on NPM or PyPI are becoming incredibly common. Attackers have realized it's really hard to hack Google or Microsoft directly because they have massive security teams.
Right.
But it's surprisingly easy to hack the lone developer in Nebraska who maintains some tiny, obscure library that it turns out Google and Microsoft both use deep down in their stack.
It's the classic weakest link theory applied to a global software ecosystem.
The source also mentions a hacked CI/CD pipeline as a major vector here.
CI/CD, continuous integration and continuous deployment. That's the automation robot that builds your code and pushes it to the servers, right?
Yes, it's the digital factory line. So imagine if the attacker doesn't attack your app. And they don't attack your dependencies, but they attack the robot that builds your app.
Okay.
They inject malicious code during the build process itself. So the final product that goes out to your customers is malware, but you don't even know it because you signed it with your own digital certificate. You thought your factory was clean.
That is it's insidious. It completely destroys trust. If I download an update from a company I trust, I assume it's safe. But if their factory was hacked...
That is the takeaway. Modern attacks are defined by these supply chain vulnerabilities. The question is no longer just, is my code secure? It's, is the code of the thousands of strangers I implicitly trust secure?
It really feels like we are moving from a fortress mentality, build high walls, to an ecosystem mentality. You can't just guard your own gate. You have to vet every single supplier who enters that gate.
You have to check everyone's ID, even the pizza delivery guy.
Yeah.
Especially the pizza delivery guy.
Moving on to segment 4. We're calling this the shifting middle. These are the familiar faces that are moving around on the board. Let's talk about cryptographic failures, AO4.
Right. This one actually moved down the list. It used to be higher up.
Which, on the surface, sounds like good news. Are we getting better at crypto?
It is good news, cautiously. AO4 covers all the classic encryption mistakes, things like using weak hashing algorithms for passwords, failing to use HTTPS across your whole site, or and this is a bad one, hard coding secrets like API keys directly into your public-facing scripts.
So why the drop? Are we just all getting smarter about encryption?
The source offers a bit of a silver lining here. It says developer awareness has improved slightly, which is true, but mostly the tools and the platforms have gotten better and are forcing our hand.
I feel like browsers helped a lot with this, right? If you don't have HTTPS now, Chrome or Firefox basically screams at the user with a big red "not secure" warning.
Exactly. The ecosystem forced the upgrade. It became bad for business to not use HTTPS, and modern coding frameworks have also gotten much smarter.
How so?
Well, it's actually harder to implement bad crypto now than it used to be. In the past, you kind of had to roll your own hashing algorithms, which is always a recipe for disaster unless you're a PhD cryptographer.
Right.
Now, most modern frameworks handle password hashing for you securely by default. You actually have to go out of your way to do it wrong.
But we aren't perfect, but the guardrails are just higher and more robust.
Right. And let's be clear, while it's lower on the list, if you fail here, the damage is catastrophic. So it's still absolutely critical. But as an industry, we are getting a little better at it.
Okay, next up in the middle pack, injection, AO5.
The absolute classic, the cockroach of the internet. It just never dies.
This includes the famous SQL injection, but also things like command injection, NoSQL injection. I feel like I've been hearing about SQL injection since the 90s.
You have. And the source has a very clear warning. It is still alive. It has not gone away.
For those who might need a quick refresher, what is the classic example the source quotes? The one that everyone learns on day one.
The classic of classics is the little string of text, or R1, OOL1.
Just that. A single quote, the word OR, and some numbers and dashes.
It's devastatingly simple. If a website login form asks for your username or your password, and you type that little string in instead, you are basically playing a logic trick on the database.
How does it work?
You are telling the database, give me the user whose password is an empty string, OR. Give me everything where the statement 1 equals 1 is true.
And since 1 always equals 1,
The database says true, that statement is always true, and it dumps the entire user table. Passwords, emails, credit card numbers. It blindly follows the logic you injected.
so why has this reduced in ranking if it's still so effective?
Again, it's largely because of better tools. The source specifically mentions ORM's object relational mapping libraries.
And what do they do?
They act as a safe translator between the developer's code and the database. They don't let you mix code and data anymore. If you try to input OR111, the ORM treats it just as a piece of text to be searched for, not as a command to be executed.
So the robot translator sees the trick and neutralizes it.
Usually. But, legacy code exists, lots of it, and people still write raw SQL sometimes because it's faster for complex queries, or maybe they just don't know any better. So it's fading, but it's definitely not dead.
Rounding out this middle section, we have AO6, insecure design.
This is a fascinating category and a very important one because it's not about code errors at all. It's about logic errors. It's about the fundamental architecture of the application.
The core concept here is that security wasn't thought about at the design level, at the whiteboard stage.
Right. And because of that, you can't patch it with a line of code later because the code is doing exactly what it was designed to do. The design was just fundamentally flawed from a security perspective.
The examples the source gives here are really, really relatable. My favorite was unlimited OTP attempts.
Yes. Think about it. If you design a forgot password system that sends a 4-digit one-time password to a user's phone, but you don't put a limit on how many times I can try to guess that code.
I can just write a simple script to try 0000, then 00001, then 00002, all the way up to 9999. It'll take a few minutes, but I'll get in.
Exactly. The code that checks the number works perfectly. It correctly says, nope, wrong number, 9,999 times, and then it correctly says, yes, right number on the last try. The code didn't fail.
The design failed.
The design failed because it didn't ask the question, should we allow 10,000 guesses in 1 minute? Should we maybe lock the account after 5 tries?
That's a great distinction. The code is bug-free, but the feature itself is insecure. Another example they gave was no rate limiting.
It's the same principle. If you build an API, but you let a single user hit it 1,000,000 times a second, your servers are going to fall over. That's a design flaw. You don't design for resilience or for abuse.
And the fix here is interesting. The source really emphasizes that the fix must happen in the design phase.
You have to build the house with fire exits from the beginning. You can't just try to drill them in after all the concrete is set. You need to do something called threat modeling before you write a single line of code. You have to think like an attacker from day one.
Well, let's move to segment 5. We're looking at authentication and integrity. AO7 is authentication failures.
Right, and this is distinct from AO1, broken access control, which confuses a lot of people.
Oh,
AO1 is about what can you do once you are in. AO7 is about can you get in at all. It's about breaking down the front door, not what you do once you're inside.
so the scope here is login systems and session management.
Correct. And the biggest offenders listed are still the classics, allowing weak passwords and not enforcing multi-factor authentication or MFA.
You know, it always surprises me that weak passwords is still listed as a developer problem. Isn't that a user problem? If I, the user, choose password 123, isn't that my fault?
Ideally, yes, it is. But it becomes a developer problem if the system allows the user to set password 123 as their password in the first place. It
Exactly.
becomes a developer problem if the system doesn't demand MFA for sensitive actions. If you run an online bank and you let people use 4-character passwords with no special characters, you are being negligent. The responsibility is on the builder to enforce good security hygiene.
And the source identifies this as the main reason for account takeovers.
Absolutely. At the end of the day, if I can guess your password or if I can steal your session cookie through an attack like session fixation, I become you. And unlike some of the complex supply chain attacks, guessing passwords is easy and cheap for attackers.
Paired with this is AO8, software and data integrity failures. This sounds very similar to the supply chain issue we talked about in AO3.
It is the first cousin of the supply chain problem. In fact, they overlap quite a bit. AO8 is about blindly trusting the integrity of code or data without any verification. It's really about the mechanism of trust itself.
The definition here mentions failing to perform checksum validation. Can you explain that to a layperson? What's a checksum?
Think of a checksum like a digital wax seal on an old-fashioned letter. When the author sends the file, they run it through a mathematical function that generates a unique stamp, a long string of characters. That's the checksum.
Okay.
If you, the recipient, download that file, you can run the same function on it. If even one single byte of that file was changed by a hacker in transit, if they added a tiny virus, the seal breaks. The string of characters you generate will be completely different.
So AO8 is simply not looking at the seal.
Exactly. It's receiving the letter, seeing the wax seal is broken, and just opening it and reading it anyway. Or even worse, not even checking for a seal in the first place.
And this applies to other things too, right?
Yeah.
Like using untrusted plugins.
Yes. Or having your CI artifacts, the files your build system creates, tampered with before they are deployed to production. It's all about verifying that what you think you are running is what you are actually running. The mantra is trust but verify.
Okay, we are getting into the deep end of the list now. Segment 6 focuses on visibility, and the second of the brand new newcomers. Let's start with AO9, logging and alerting failures.
This is what I like to call the ghost in the machine risk. The scenario is simple and terrifying. An attack is happening right now on your systems, but absolutely no one knows.
Because the system is completely silent.
Exactly. If a tree falls in a forest and no one logs it, did it make a sound? In the world of security, if a hacker tries to brute force your admin panel 10,000 times and no log entry is generated, you are completely blind.
The source mentions no logs for brute force attempts or just having no alerts configured at all.
Right. Or having logs, but they're scattered across 100 different servers with no way to correlate them. Or no integration with a SIEM security information and event management system. You need a central brain that collects all these logs and looks for suspicious patterns.
So the burglar's in the house, maybe they're picking the lock, maybe they broke a window, but you never bothered to install a motion detector or an alarm system.
And the consequence, as the source points out, is something called attacker dwell time. This is a really scary metric for security professionals.
Dwell time.
It's the length of time an attacker stays inside your system, undetected. Weak detection means that dwell time can be enormous. We are talking weeks, months, sometimes even years.
Years.
Oh yes, there are famous cases of this. They can leisurely explore your network, steal data very slowly so no one notices a big spike in traffic, and plant backdoors so they can get back in later. If you don't have logs, you can't even investigate how they got in after you finally find them. You can't close the hole.
Visibility is everything. But let's talk about A10. This is the second brand new category for 2025. Mishandling of exceptional conditions.
This is a very subtle and nuanced addition to the list, and I think it's a really smart one. It's all about what happens when things go wrong.
Mishandling of exceptional conditions. It sounds a bit technical, a bit dry. What's the core concept?
It's about failing to handle rare cases, or errors gracefully. See, every application runs just fine when the user does exactly what they're supposed to do. We call that the happy path.
Uh,
But what happens when the server's disk fills up? What happens when the network connection drops in the middle of a transaction? What happens when a user pastes the entire text of War and Peace into a field that was expecting a zip code?
the source gives a great, very common example, stack traces leaking.
Yes, I'm sure everyone has seen this. You click a button on a website, the page crashes, and suddenly you're looking at 50 lines of what looks like computer code on your screen. Something like fatal error at line 42 in var delta whtml database connection.php.
It just looks ugly and broken to a normal user. It looked like the matrix just glitched.
It looks ugly to the user, but to a hacker, it's a treasure map. It tells them the exact file structure on your server, the type of database you're using. Is it MySQL, PostgreSQL, the names of your variables? It's TMI too much information. It helps them craft their next, more targeted attack.
Another example they give is sensitive data being exposed when an app crashes.
This one's really dangerous. Imagine the app crashes while it's processing your credit card transaction. In order to help the developer debug the crash, does it dump the computer's memory to a log file?
And if it does,
Does that log file now contain your unencrypted credit card number because the crash happened before the encryption step could complete?
ooh, that's bad. So the crash itself actually bypasses the security controls.
Exactly. And the source notes the reality here. These kinds of bugs usually explode, or fat-te-hein, as the source vividly puts it, in production environments when real users start doing unexpected things. You can't always predict them in a clean testing environment, because testing usually follows the rules. Real life breaks the rules. You need to build robust handlers for the unexpected.
So we've covered all 10. We've seen the kings, the risers, and the newcomers. Let's move to our final segment, segment 7, the 2025 mindset and the hunter's perspective.
Right. We need to step back from the individual trees and look at the whole forest. What is the brain, the central thesis of this update? If you look at all these changes together, AO2 rising so dramatically, AO3 appearing out of nowhere, the emphasis on AO6 and A10 there is a very clear pattern emerging.
What are the 4 pillars that the source identifies as the core of this new focus?
The OWASP 2025 focus is clearly on 4 things. 1, cloud and DevOps mistakes. 2, software supply chain attacks. 3, design-level security. And 4, detection and response.
It really feels like we are moving away from a world where the primary concern was the coder forgot a semicolon, to a world where the concern is the architect built the entire foundation on sand.
That is the perfect summary. We are moving from syntax errors to structural failures. We are moving from just code security to a much broader concept of product security.
Now let's flip the script, because this is the fun part. We know a lot of our listeners are interested in bug bounties. They're the ethical hackers who get paid to find these flaws. The source explicitly includes a bug bounty POV. So where's the money in 2025?
If you are a hunter listening to this, pay very close attention. The high-value targets are shifting. The source lists access control bugs and API authorization as still being top tier.
Because they're just ubiquitous, like we said back in AO1. They're everywhere.
Right. If you want a consistent, steady payout, look for IDORs. They are in almost every complex application. But then it gets interesting. It lists CI/CD leaks and dependency poisoning as high-value targets.
How does a bug bounty hunter even find a CI/CD leak? That sounds like an internal problem.
They look for those exposed.env files we talked about earlier. They write scripts to scan public code repositories like GitHub to see if a developer accidentally committed a secret API key. They analyze public build logs. It's not about hacking the running app. It's about hacking the process around the app.
And business logic flaws.
That's the insecure design part we covered in AO6. Finding a way to buy an item for $0 because the application's logic didn't properly check for negative numbers in the quantity field, or finding a way to apply a coupon code 50 times to the same order. That is where the really big 6-figure payouts are, because those flaws hurt the business's bottom line directly.
It's a perfect synthesis, isn't it? The hunter list almost perfectly mirrors the top risks on the main list. It's particularly emphasizing API, supply chain, and CI/CD issues.
Of course.
That's where the industry is hurting the most, so that's where they are willing to pay the most for Band-Aids.
Exactly. Follow the pain to find the value.
We're coming to the end of our deep dive. Let's do a quick summary. What is the single major takeaway for our listener today?
The takeaway is evolution. We are evolving from a world of simple, line-level code bugs like SQL injection to a world of complex, interconnected architectural and supply chain failures. You cannot just code your way to security anymore. You have to design for it, and you have to verify the integrity of everything and everyone you trust.
And a final call to action for everyone out there building things.
Remember, this is a preview, a forecast. The landscape changes incredibly fast. But the key principle is to stop trusting defaults, change the default configurations, and stop trusting third-party code blindly. Verify everything. Scan your dependencies, lock your doors, and make sure you know who you're giving keys to.
I want to leave everyone with a final provocative thought, something that really struck me when we were talking about insecure design AO6. If the fix for these major flaws has to happen before the code is even written, if the flaw is in the business logic itself, does that mean security is no longer just an IT problem or an engineering problem?
It absolutely isn't. Not anymore.
It sounds to me like it's becoming a product management problem. If the product manager asks for a feature that is inherently insecure, like make the password reset process really, really easy with no extra steps, then the eventual security breach is their fault, not just the coders.
That is the uncomfortable truth that a lot of companies are going to have to face in 2025 and beyond. Security begins on the whiteboard, not on the keyboard.
Security begins on the whiteboard. I love that. Thank you so much for guiding us through the storm clouds of 2025.
Always a pleasure to check the forecast with you.
And to our listener, thanks for swimming in the deep end with us. Stay safe, check your dependencies, and we'll see you on the next deep dive.
Goodbye.